The problem set that I can clear up? No, not yet. No. Why do you have concerns about it, or you're just curious? Okay. No concerns about whether it's solvable, though, are there? That's what I don't want to hear. It looks very. I don't have any concerns about that. Yeah, but there's so many equations, like you're bound to get something wrong somewhere, and so you put one negative one where it should be a positive one, and everything
I
goes
put all
haywire.
5 attempts at mine in there,
Did you?
and they're still slightly spinning.
Oh, they are.
Yeah,
Okay.
but they're close.
Well, yeah, that's not a good trait in a bicycle frame. You don't want it to be constantly spinning.
Well, unless it's the tire.
Yeah, right. But this is not the tire.
No, not the frame.
Um, yeah. Any questions on stuff that I mean we could work through part of a problem for one member if you'd like. If anyone has a, um, but I need to know some external loads, I guess. And nobody's. Yeah. All right. Well, actually, let's. Why don't you just come talk to me after if you have questions and yeah, I don't have anything sitting in front of me to go through it. So, all right. So let's go on to the example that I mentioned last time. So we have a left-handed screw supporting a weight of 10,000 newtons. And the left-handed screw means the threads look like that. Well, you know. Um, the radius from the center of the screw to the outer edge of the thread, I think I gave that to you as 0.1 meters, but that doesn't make any sense. I meant, I want, meant, yeah, so let's, oh, 10 millimeters. Okay. Well, when I solved it, I did it for 100 millimeters. So, but yeah, this is a centimeter. I know exactly. Yeah, it's like this big. Um, so this makes more sense. And then we're turning it with this crank arm that's the distance from the edge of the arm to the center of the screw is 25 centimeters, 0.25 meters. Um, the coefficient of static friction, we'll assume this is steel and steel, so we'll um, use 0.7 as the coefficient of static friction. And we'll use a lead of 5 millimeters, so 0.005 meters. And that's this distance. And we want to know how much force you have to apply to the end of this crank to make this screw raise. Okay. Um, to the end of the lever arm. Okay. So first of all, with this left-handed screw, which way do we need to rotate this screw? think of looking at it from the top. Do we have to rotate this clockwise or counterclockwise to lift it? Okay, I have to think about that. So counter left hand rule. Okay. Hey, listen, shut up for a second. I need to. Okay, so righty tighty left. So it's lefty tighty righty loosey in this case. And we want loosey for it to go up. So right. Yeah. So clockwise. So what did you guys say? Counterclockwise? Oh, you did? Okay. So you were right. Okay. Good job, everybody. Except me. Okay, so to think about this motion, the first step is to think of it as this whole thread being concentrated into this one location where this distance is 1 centimeter. And it's sliding up a ramp that's going this way. And so if you think of the perspective of the all-seeing eye, what you have is this block sliding up an incline facing this way, right? It's not a very good incline. Thanks. Okay, is everyone following that? That makes sense? So we have this angle theta, and we have a force acting down of 10,000 newtons, and a force acting, we're trying to get it up this ramp, so we have to apply a force of Q this way to get it going. And we're going to calculate that force Q. The coordinate system we're going to use is rotated with the ramp. And how do we figure out what that angle is? That's right. Yep. So this angle is, so the tangent of this angle is this height, you know, over one circumference, so lead over 2 pi r. So we got inverse tangent of the lead. Oh, I have that wrong too. I have that way wrong. Oh, I guess I'm just doing it in millimeters. Okay, so 2 pi times the radius, 10 millimeters. Okay, yes. Yeah, you're right. Yep, you're right. And so could someone calculate that? 1.39 degrees. So now we can go to the free body diagram. The forces, we have a downward force of 10,000. And this angle is 1.39. This angle is 1.39. We have the horizontal force of Q. And this angle is 1.39 degrees. And then we have normal force. And which way is the friction force acting? Down the ramp, yep. and we are right at the point where like the friction force is maxed out, right? The static friction force is as high as it can get before it starts to slide. That's what we're looking for. So we can just replace this friction force with the coefficient of static friction times the normal. So Newton's second law says 10,000 times sine of 1.39 degrees, and then negative 10,000 cosine 1.39 degrees. Plus negative q times cosine of 1.39, negative q times sine of 1.39, plus, so this is in the positive x direction, so 0.7 n, and we're right at the point where it's about to start moving, but so the acceleration is still 0. So all my numbers are wrong because I used the wrong angle here. Could someone calculate for 10,000 sine 1.39?
Oh, did I do it wrong?
Oh, really?
Oh, I did it wrong.
Okay. So what is it? Okay. So that goes in all these places. That's all right. We all have these electronic pens, so erasing's easy. Okay, so let's just rewrite this equation. We can solve it as a matrix equation. So what's 10,000 times sine of 4.55? Okay, and what's cosine of 4.55? Okay. And what's 10,000 cosine of 4.55? Oh, wait a second. Something went wrong here. So this is just 0.99, right? What did you say? Like 0.997, right?
Yeah.
Okay. And so this one over here then is. Oh, you were doing the one below.
Yeah, 10,000 times cosine 4.55. So give you
Okay. 9968, did you say?
9968.5, yeah.
Okay, 0.5. And then sine of 4.55 is point 0.0793, I guess, or and then this is n. Does that look right? Oh, yeah. It's incomplete Q. Okay, so we can write this in a matrix form as negative 0.997, 0.7, negative 0.0791 times Qn is equal to negative 793.3 and then positive 9968.5. Can someone calculate that, figure out those values?
There 8,252
Okay.
and 10,620.
Okay. So that's not what the question's asking for yet. We're pretty much done, but this is giving us the force pushing this up the ramp, right? And that doesn't represent really anything physically important to us. We want to know, like that's if instead of applying a force to this lever arm, you just you had a little place you could push your thumb on the side of the thread, and that wouldn't be a very efficient way to turn a screw. So we need to go from this force Q to the force that would have to be applied at the end of this lever arm. Okay, so think of it just in terms of you're applying couples. Okay, so we just have to figure out what the torque is, what the moment is produced by that force Q, and then figure out what force needs to be applied to the end of this lever arm to produce that same torque. Okay, so that force Q, what's its lever arm?
5 millimeters.
Right, it's the radius of that screw. Okay, so we have Q times the radius is equal to the force we're trying to find times the lever arm, 0.25, right? So 8252 times 0.01 is equal to F times 0.25. And what do you get for F? 330 newtons. Okay, so manageable force. Anyone have any questions about this approach? This is the type of method that you're going to have to do with these problems. I think I mentioned that last time. Like, we're not going to use formulas on this stuff that we came up with. You're just going to have to show that you can take information about the screw direction and sort of think geometrically in order to set up everything moving in the right direction, get your force of friction in the right direction. That's the stuff you're going to have to do for these problems. Okay. All right. So that's the end of square threaded screws, and now we can go on to bearing friction. I can't bear any more friction. So bearing friction, I'm going to break it into two categories. Journal bearings, which like here's a case of a journal bearing where where a rotating shaft goes all the way through. So the idea of this bearing is that it can't do anything to keep it from sliding one way or the other. All it can do is keep it from falling up and down, right? It only limits it in its position in one plane. And then that's different from thrust bearings, where you have like the end of a what am I doing here? Okay, so in this case, this shaft goes all the way through this body, but this collar on the shaft keeps it from sliding through, right? So in this case, not only is that shaft restricted from moving vertically up and down and side to side, but it's also restricted from sliding in and out of that hole, okay? And these two types of bearings, you have to calculate friction in different ways. Friction's produced in different ways. In both cases, I'm going to do the derivations assuming that first the acceleration vector is equal to zeros. Okay, so it's a statics class. And also assuming that the force of friction, the magnitude of the force of friction is equal to some coefficient of friction times the normal force. Okay, so these two assumptions hold for two specific cases, two different cases of things going on, okay? Or they can hold for two different cases. What would those two cases be? Come on, someone say the easy one, and then you don't have to sit awkwardly while I wait for someone to tell me the hard one. Okay, that's right, that's right. That's what I was thinking would be the hard one. But so you ruined my plan, but that's all right. Yeah, so the two cases are, first, if it's rotating with a constant angular velocity, okay? Then this coefficient of friction is just the coefficient of kinetic friction, okay? And the other case, but it has to be rotating with a constant angular velocity, or that acceleration equals zero doesn't apply. And the second case is that we're just at the limit of the static friction, just like motion is impending, okay? So we can't be, we're at the limit, so you still have zero acceleration, right? It's still. And it has to be the limit, because otherwise, remember, this is an expression for the maximum static friction that can be applied if you replace this coefficient of friction with coefficient of static friction. So for the force of friction to actually be equal to that maximum value, we need to be right at the limit of the, right as motion is about to start. Does that make sense? Okay. So this is valid for two cases. If the coefficient of friction is equal to mu sub k, then this works for rotating with a constant angular velocity. And second, if mu is equal to static coefficient of friction, then this rotating shaft is at rest, just about to start moving. And this is almost a super interesting topic, okay? Like these kind of bearings come up in all sorts of applications. The reason it's not that interesting a topic, unfortunately, is we're doing this assuming drive friction. Which means that what we're going to calculate does not apply well if you have lubrication, okay? And obviously, in most important engineering applications, in either of these two cases, you're going to want these bearings to be lubricated, okay? But anyways, it's a first look at thinking about these problems, and there might be some simple applications where this is useful, okay? But you know, basically, you can't apply this to things going on in a car engine or anything, hopefully, or else your car's in bad shape. So when do you talk about friction with lubrication? Like that could come up in like a fluid dynamics class. It's unfortunately mathematically pretty complicated. Okay, so let's first think about journal bearings. This is also known as axle friction. So think about I guess I'll think about it as like a shaft rotating inside a couple of bearings. Or let's think about just a shaft rotating inside a single bearing like this. Imagine that it's all balanced up nicely. And we'll assume that there's a weight applied of, a total weight of W. So you can think of these two weights of W over 2 being applied. So those weights cause a normal force between the bearing and the shaft. And that normal force causes friction. And what's the effect of the friction? The effect is that if you start this spinning, it won't just spin forever, right? Which means that in order to keep it rotating with a constant angular velocity, you need to constantly apply some couple to it, okay? So we want to calculate what the couple is that's required to keep this rotating with a constant angular velocity. So what's the required couple M to keep the shaft rotating at a constant angular velocity? All right, well, let's think about the free body diagram. We're just going to look at a cross section of this shaft. So what loads are acting? Okay, so friction is acting.
Normal force.
yeah, there's friction and there's a normal force. Let me wait to put those in. So we know, first of all, that we have this downward force W, right? And we also know that we have this couple M. Right? And we know that we want this to be in static equilibrium. So what forces are acting? There is there's a normal and a friction force. Let's think of those adding up to a single force that counteracts this W, right? In order for this to be in static equilibrium, we have to have an upward force that balances this. Okay? But what if I put that upward force here? So that's made up of, that's a combination of friction and normal force. Is this in static equilibrium? Yeah, that's right, because there's nothing balancing this moment. Okay? So that can't be. So what we have to have is this offsetting force applied at some distance from the center line. This has to be acting at some angle. I'll call this theta. And I'll call this force R, but its magnitude has to be equal to W. Yeah, you're right. Let's draw, thank you. Let's draw M going the other way, just so I can keep all these pictures the way I have them in my notes. Yeah, thanks. All right. And so now we know that this force R is acting at this point, right? And we know it's made up of a friction force and a normal force. So now that we know where it's applied, we know where the normal force is acting, right? The normal force has to be normal, or else it needs a different name, right? So it acts there. And the force of friction has to act perpendicular. And that's equal to our coefficient times the normal force. Okay, so, well, any questions about that? Does that make sense? Okay, so let's go to Newton's second law. I'm just going to use a standard coordinate system. So we have 0, negative W. No, let's not do that. Sorry. Let's not do Newton's second law. Let's just think about that. Let's think about that force R. So that force R, which is in a vector form is like this, has to be equal to a normal force, which is, so this angle is also theta. So that normal force has to be negative n times the sine of theta, positive n cosine theta. And then the friction force is positive mu times n times cosine of theta, positive mu n sine theta. And if you use the first one of these two equations, it gives you that n sine theta is equal to mu n cosine theta. Fiddle around and you can solve for theta. And so that angle is equal to the inverse tangent of mu. And by the way, in order for this to make sense, you're going to need to do all these calculations in radians. Okay, so you're going to have to use. I think that's right. You're going to have to put your calculator in radians. All right, so now let's go to the second equation. So that was the first one. The second equation says r is equal to n times the cosine of theta, and this is theta, so cosine of the inverse tangent of mu plus mu times n times the sine of the inverse tangent of mu. And now the cosine and sine of the angle with this as the tangent, we can represent that this way. Okay, so we're looking for this angle that has a tangent of mu. So opposite over adjacent is equal to mu, and that means that the hypotenuse is equal to 1 plus mu squared square root. And so the cosine of this angle then has to be 1 over this. And the sine of theta has to be mu over this. And so now plug these values into equation 2, and you get something that simplifies nicely. So you get n times 1 over 1 plus mu squared square root plus mu n times mu over 1 plus mu squared square root. So that gives you n times 1 plus mu squared over square root of 1 plus mu squared. And finally, you can just write that as, 1 plus mu squared is this square root thing squared. So you can just write this as n times 1 plus mu squared square root is equal to r. Okay, so we know that the value of m has to be equal to r times this distance, right? And that distance, that moment arm of r, is just the little radius here, the radius of this axle, times the sine of theta, right? So m is equal to r times little r sine theta. And that is, so r is what we just calculated, normal times 1 plus mu squared square root times little r, and then sine theta we calculated over here is mu over square root and a bunch of stuff cancels. These cancel. And you just end up with this super simple expression, mu r normal force. That normal force isn't the simplest thing in the world to measure directly. So notice that if you have really low friction, that normal force is going to approach the big R force, right? Like that big R force is the friction force vector plus the normal force vector. And so if that friction force vector is little, you get closer and closer to R and N being the same thing. So if the friction is low, you can approximate the moment required to keep this rotating with a constant angular velocity as R times little r times the coefficient. Okay, so this approximation is, it's given in the book. This is the exact formula. And actually, this approximation is not ever necessary to use because we can come up with an exact formula for n in terms of r. So where did I do that? And I guess I'll show that in this example problem. The next thing I'm going to do. Anybody have any questions about any of that before I go on to do an example? Follow all the steps, okay? Okay, so let's do this problem. What's the cutoff value of mu so that approximation, the moment is about equal to big R, little r, mu, is accurate within 5% of the true value of that required couple. Well, think about that right triangle that makes up this R vector. So there's R. There's the force of friction, which is equal to mu n. And there's n. And this problem comes down to this question. What's the mu required so that the approximate value, the approximate value of the couple divided by the exact value of the couple and you can see you get cancels here, and this just becomes R over n is equal to, so what am I looking for this to be equal to if this is accurate within 5%? So actually, we want them to be about the same, right? So it's either going to be 0.95 or 1.05. And which one do we want in this case? Which one would it be? You can tell from just looking at that triangle. We have the hypotenuse over, so it's yeah, it's going to be 1.05. Okay, so let's first use just the Pythagorean theorem to come up with the relationship between R and n. We know that R is equal to mu squared n squared plus n squared, all square root, right? This is the right triangle. And you can rearrange that. These both have an n squared, so you can distribute that out and then just pull out a single n. And then you have n times 1 plus mu squared, all square root. So now replace the R here with this expression. And you have, so R over n is equal to n times 1 plus mu squared, square root, over n. You get a cancellation. And this requirement just says the square root of 1 plus mu squared has to be equal to 1.05 at this cutoff. And so now solve for mu, and you get that if you want 5% accuracy from that approximate formula, mu has to be equal to less than 0.32. More importantly, what we can see from doing this is that we can express the normal force in terms of R, right? The normal force is always equal to R divided by 1 plus mu squared, right? So instead of using this approximate formula, so we don't have to figure out what the normal force is, we can just substitute that other expression for the normal in, and give an exact expression in terms of R. So let's see. So the moment exact formula is mu R normal. and that's equal to mu times R times big R over square root of 1 plus mu squared. Anyone have any questions about that? All right. And then the last thing we're going to talk about in friction is, what did I call them? Thrust bearings. So think of a case like this. You have this hollow shaft rotating, like rubbing on, you know, some kind of end, some kind of ground thing here as it rotates. And so this is the shape of the contact. And there is a force pushing this end piece and this shaft together. I'll call that N. And there's also a couple, M, that's required to keep this moving with a constant angular velocity. That's the same idea as the last one. And I'll call this inner radius R inner, and the outer radius R outer. Oh, by the way, both of these are derived in different ways in the book. If you're curious, if you like trying to fiddle through like integral stuff and whatever, especially, you know, this one, I use a different integral approach than they do. Okay, so what we want is the same thing. We want to calculate the couple that has to be applied to keep this rotating with a constant angular velocity. And so let's look at the geometry of the point where these are in contact, okay? So you have an inner radius and an outer radius. And we're going to assume that this force N is distributed evenly over the whole surface area that's in contact, okay? So let's say, let's define the pressure as the total normal force divided by the area in contact. So that's N over 2 pi times r outer squared minus r inner squared. And now, well, where am I going with this? I'm about to set this up as an integral. Why do I need to do this? What makes this different than just a block sliding along an incline or something?
More leverage on like against the friction or whatever on the outside.
Exactly. Yep. So right, this friction is providing a couple, right? And the way it provides that couple, I should say, is that even though the friction force is constant everywhere, right? The moment produced by it has a small moment arm close to the center and a big moment arm far from the center. And so you get this uneven distribution of contribution to the couple based on where you are. Okay, you see what I mean? Like far from the center, you get a big moment. Close to the center, you get a small moment. So I'm going to define an increment of area, dA, that depends on the distance from the center. And then the force on that increment is just going to be the pressure times the area times dA. Okay? And then based on that force, we'll calculate the moment, integrate up, and see what the total moment is. Okay, so dA, I'm going to define as a infinitesimal ring. And what's the formula for that increment of area? How do you calculate that area? The easiest way to do it is to think of stretching it out into a thin rectangle, you know? So it's the circumference times the thickness. Okay, so circumference is 2 pi r, whatever r we're in, and the thickness is dr. That's our increment. Yep, that's going to be our variable. And so that means that the total force acting on dA. Now, of course, this is going to be an infinitesimal force, right? Because it's an infinitesimal area. Is the pressure times dA. So N over 2 pi r outer squared minus r inner squared. That's the pressure times dA, so times 2 pi r dr. Get some cancellations. And you get a final formula. Ooh, I lost my... What did I lose? Oh, sorry, I didn't... Pi r... This is not the formula for area. This is a bastardized formula for area / circumference. Something I'm working on in my spare time. Okay, no, don't use that formula for area. Okay, there's no 2 in the area formula. So this, is that the only place? Yeah, so that 2 doesn't cancel. The pi's cancel. So you get 2 times n times rdr over r outer squared minus r inner squared. And that's the force. And now how do I calculate? So now for a single increment, a single little ring, we can calculate the force. So how would we calculate the moment produced by that little increment? And let's calculate it around the center. Like, what's the moment arm of? We calculated the force. That force all has the same moment arm. What's the moment arm? R. So you can think of that as the increment of moment is equal to P times R dA. So 2n r squared dr over r outer squared minus r inner squared. And now how do I calculate the total moment? Yeah, just integrate from all, we only have one variable, r, so what are our boundaries for r? Yep, inner to outer. So total moment is r inner to r outer. I guess I'll pull all the constants out first just to unclutter things. So these things all can come outside. They don't vary. Times the integral from r inner to r outer of r squared dr. So you get 2 pi n over r outer squared minus r inner squared times 3 in the denominator, r to the third, evaluated from r inner to r outer. And so the final formula is the moment is equal to 2 mu normal times r outer cubed minus r inner cubed over 3 over r outer squared minus r inner squared. That's been there all along. That was, where did the mu come from? Yeah, okay, I just forgot to write it, I guess. So this force that we're talking about, this force increment, is produced by the friction, right? So it's not the normal force. I mean, I guess, okay, so, all right. So let's, yeah, I wasn't careful here. So the first you can think of calculating the force increment on dA, and there are two different forces, so we have to figure out which one we're talking about. So first, let's think about the increment of normal force acting on that little ring, okay? this is the increment of normal force acting on that ring. But now if you want to figure out the moment produced, that moment isn't produced by the normal force, it's produced by the friction force, right? And the friction force is mu times the normal. So this is the point where you'd have to get mu in there. So yeah, I think that's a good way to think about it. Think of what we calculated here was the increment of the normal force acting on that ring. Once we know that normal force, we can think of this as we can think of that as the moment produced by the increment of the friction force around the center, and that's equal to the increment of friction force times r, which is mu times p d area times r. Sorry, that was sort of a mess.
Go down again.
Yeah. But does that make sense, the way that I was just describing it? So first we figured out how much normal is on that thing, because we can't figure out how much friction is acting on that little ring until we figure out how much normal force is acting on it. So that's what we did first. And then we plugged that normal force in, because we know the friction force is mu times that normal. Then we could go to calculating the moment. Anyone have any questions about this? Okay, well, that's all I want to say about friction. So, what did I say we're going to do next? We are going to do, oh, I don't think I said yet. I need to think about that. So there's one chapter, I think, on moments of inertia, or else we might just jump straight to the last chapter in the book, which is the virtual work, which is, I know, a common way of doing statics problems in civil engineering. So anyways, this is the end of this chapter. I'll get some practice problems up. I need to get solutions up to the practice problems you have. And yeah, come ask questions if you have questions about the problem set. I'll see you Tuesday.